Welcome back to the workshop. We want to continue taking a look at section 4.1, graphs and their representations. So one of the things about the representations of graphs is that there are a lot of ways to do it. So since there's different ways that we could draw a graph, we want to recognize that sometimes two graphs are actually equal to one another, even though they're the same. Or sorry, two graphs are equal to one another. They're the same graph, even though they're drawn differently. That's what I wanted to say there. So that's what this example considers here. It actually works out that the graph H1 and the graph H2 are the same graph essentially. So the idea of sameness changes between contexts. Okay, saying that two numbers are equal is a little bit different than saying two squares are equal. While we know what we might mean in each case, right, they have something a little bit different behind them. Okay, so here we want to look at the idea of sameness in graphs. So these are the same, essentially. If we were to ignore all of the labels, just ignore the labels, what we can observe is that we have a triangle on top of a square. And the square looks a little bit funny here, but it's still a square or a rectangle, that's fine. So triangle on top of rectangle, triangle inside of rectangle, inside of twisted rectangle. Okay, so let's identify the triangle. So here's our triangle. And here's our triangle. And then we also have a square or a rectangle here, four-sided shape. Okay. And here, our four-sided shape, those sides are kind of bent and twisted, which is perfectly fine. There's no actual problem with that because I don't care if the edges are straight or not. It's fine that they're not. So these represent the same thing because I've got a square and a triangle, a square and a triangle. Sweet. So can we draw another one that represents the same thing? Yeah, we can. There's loads of them. So here, if I wanted to, I could take my 5 vertices and arrange them in this way, and I could give them different labels if I wanted to. A, B, let's call this one C, D, and E, not that it matters. And then I could join them, giving myself a square and a triangle. Bam, there it is. So this one, it looks like all I did was take that top corner, right? It looks like an envelope. You fold it down to close the envelope. There you go. Same thing, right? Excellent. So this is another representation of the exact same, whatever it means to be the same graph. Okay? But that's ignoring what the labels are. Because the labels are just ways to refer to a vertex. Okay, it's a little bit weird. So earlier I said that I said the vertex is the letters and the dot represents the letter, which is true, but I suppose it's the other way as well. I could label these differently and I'd still have the same graph. Okay. So what does it mean to be the same for graphs? Well, a graph G1 is said to be isomorphic. Okay, isomorphic is the idea of equality when it comes to graph. They're isomorphic, they're the same. Now let's get this color correct here. They are the same. Okay, so they're said to be isomorphic, denoted by graph 1 and graph 2. We usually want to say equal to, but since we don't actually, we're not actually working with equality, we don't want to confuse our symbols here. We use equality with kind of a tilde above it. So this symbol represents isomorphism, an equal sign with a tilde above it. So a graph G1 is said to be isomorphic to a graph G2 if there exists a one-to-one correspondence, call it F, from the set of vertices in the first graph to the set of vertices in the second graph, such that whenever two vertices are adjacent in the first graph, then they're also adjacent in the second graph, and vice versa as well. If they're adjacent in the second graph, they're adjacent in the first. Okay, the function f is called an isomorphism. So an isomorphism is the function which takes one graph to another and shows that the two graphs are isomorphic. Okay, so isomorphic, two graphs are isomorphic, and that the idea of them being isomorphic is given by an isomorphism, the function that takes the vertices of one to the other. So let's see here. To present things just a little bit differently, let's take a look at this. So we want to say that the edge UV is in the edge set of G1, right? This is an edge here if and only if, when we look at the image of those, right? Here's two vertices. The function f takes the vertex set from G1 and sends it to the vertex set of G2. So this edge, which joins these two vertices, is in the edge set if and only if this edge is also in the edge set of the second graph. Okay, so that's what we're saying here. What does that look like? We'll take a look at that in this example here, right? We're going to revisit this guy. But to remind ourselves of one more thing, let's also remember that the function f, which we're saying goes from the vertex set of graph 1 to the vertex set of graph 2, okay, this function is a one-to-one correspondence, which means it is one-to-one and onto. Okay, so it has both of those qualities. So that's an isomorphism, takes vertices to vertices. So let's do that for these two graphs here. I scribbled out all of those labelings. Let's go ahead and keep them. And what I want to do is I want to take this triangle and I want to map it to this triangle. And then I want to take this square and map it to the square. So I'm going to take H1 to H2. So I've got my f. Let's see here. I've got my function f, which takes the vertex set of graph H1 and sends it to the vertex set of graph H2. And what I want is I want to take the vertices. So I want to find outputs for P1, Q1, and R1. P1, f of Q1, and f of R1. That's my triangle, P1, Q1, R1. So I want to look at that over here. So P1 and Q1 are adjacent, P1 and R1 are adjacent, R1 and Q1 are adjacent. So that's the adjacencies that I'm preserving by mapping this triangle to that triangle. So I'm going to send P1 to R1. That makes sense. That's the peak of the triangle there. So P1 goes to, P1 goes to R2. P1 goes to R2. And let's see here. I've got some options here. Q1 can go to S2 or Q1 can go to P2 because I've got some symmetry here. So I'm going to send Q1 to S2. Send Q1 to S2. Which means that to complete my triangle, I have to send R1 to P2. R1 goes to P2. Excellent. From here, I need R1 to be adjacent to, R1 is adjacent to T1. So I sent R1, I'm forgetting stuff already here. Where did I send R1 to? R1 sent to P2. So let me draw that here. R1 got sent to P2. So I need T1 is adjacent to R1, so I need the image of T1 to be adjacent to P2. What's adjacent to P2? T2. So f of T1 is T2. And then there's only one vertex left, but I should make sure that I've got it all correct here. S1, I'm saying should go to Q2, and it should be adjacent to the image of Q1, and it should be adjacent to the image of T1. So Q2 should be adjacent to the image of T1, which is T2. And Q2 needs to be adjacent to the image of Q1, which was S2. Perfect, it is. So Q2 is the image of S1. Excellent. This is an isomorphism. On these simple examples, it doesn't take much, right? Since I'm defining it, I'm defining our isomorphism by the individual points, right? It's piecewise defined by 1, 2, 3, 4, 5 pieces. And this is fine. This is a perfectly acceptable way to define our isomorphism. It shows that it's one-to-one because each output only has one input. This is the only output of R2. It's onto because it goes onto all 5 vertices. So it is a one-to-one correspondence, and we created it by choosing things that would be adjacent. Okay, so we preserved adjacencies in our creation of this isomorphism. All right, so one more example. Let's show that these two graphs are also isomorphic. So one more example where show these two are isomorphic. In this case, we're going to call the isomorphism phi. We're going from the vertex set of G1 to the vertex set of G2. Excellent. So let's take a look at this a moment. Again, what we're going to do is we're going to determine the images of the vertices, so individually. So V of U1 is equal to something, phi of U1 V1 is equal to something, U1 V1, phi of W1 is equal to something, phi of X1 is equal to something, phi of Y1 is equal to something, and phi of Z1 is equal to something. Now I can't just choose these arbitrarily. Okay, I have to make sure that the adjacencies are preserved. And there are a lot of options. There are actually 4 different isomorphisms that we could identify between these two graphs, going from G1 to G2. So what I'm going to do is I'm going to think of it as taking this whole thing and turning it up. Okay, so what I'm going to do is I'm going to take this square and bring it up to the top here. And what I can do is I can identify that I've got the square right here. So I've got a square and a square. Let's take a look at this other square. So I've got 2 squares, and I just want to preserve these squares. So the top square is going to go to the top, and the left square is going to go to the top, and the right square is going to go to the bottom. And that gives us these 2 squares, okay? But essentially what happened is I turned it up, I leave these, right? So I end up with this, U1, X1, Y1, Z1, and V1, W1. But then I go ahead and I twist these 2 and twist these 2. So I've got Y1 and V1 still connected, but I've twisted the top So that way it looks like this. And I've twisted the bottom, W1 and Z1, so it looks like this. Okay, so what I'm doing here is I'm identifying these two graphs, right? They look the same in X and X and X and X. It's perfect. So what I'm going to do is I'm going to send U1 to U2. I'm going to send well, yeah, this is fine. I'm going to send V1 is here, to X2. I'm going to send W1, which is over here, to Y2. I'm going to send X1 up here to V2. I'm going to send Y1, which is here, to W2. Speaking of W2s, it's almost tax season when I'm recording this video, or it is tax season, so make sure you do your taxes. Unless it's November when you're watching this, then worry about that in a few months. All right, Z1, which is right here, I'm going to map that to Z2. Excellent. This is an isomorphism. Why is it an isomorphism? Well, it's one-to-one because each output only has one input. And it's onto because all of U2, V2, W2, X2, Y2, Z2 appear, right? Everything appears. So it's one-to-one and onto, but it also needs to preserve adjacencies. And I did that by manipulating this graph to look like that one. So then I just had to identify the one in the top left goes to the one top left, one on top right goes to the one on top right, and so on. Okay, easy, pretty straightforward. You may not have done this. You don't need to do this at all. All you need to do is find your own identification from here to here. And if you have to draw these out, cool, whatever. If you don't need to draw them out, don't worry about it. All that we're looking for in this case is the isomorphism. These are isomorphic. How do I know? Because here is an isomorphism. Excellent. So that's all I wanted to share in this video. And the next one will continue to look at isomorphisms, but in particular, we'll look at some situations where things are not isomorphic. And we'll look at how to show that two graphs are not isomorphic, that they're not the same. So thank you for your time. I'll see you guys back in the workshop in just a little bit.